When we're looking at our nucleophilic additions, this is really a nucleophile being added to a polar pi bond. We really have two primary conditions under which we can run. And these two conditions are shown below in kind of a brief summary. What we need to identify are our primary differences. If we take a look in the top reaction, we're starting with a nucleophile, or a negatively charged species. Okay? And in the bottom reaction, we're actually starting with a positively charged species. So this may seem a bit bizarre at first, but what we just have to go through and do is identify what that difference means. So we're looking at a strong nucleophile to start, and we're looking at, come on, pen, we're looking at a strong acid to start. Okay, and these are kind of counterpoints. Well, what benefits do we get in each one? Well, if we look at the strong nucleophile situation, really what we're doing is we're speeding the reaction, okay, or spedding, depending on how you want to pronounce that, by increasing the strength of the nucleophile. Okay, we have a strong one. Whereas in our second reaction, if we look at the nucleophile, it's a weak one because it's uncharged. In our second reaction, we're going to speed it, okay, or frickin' sped, by adding an acid. And that may seem a bit bizarre because if we're thinking about our nucleophilic additions, we're adding nucleophiles to electrophiles. So the reason it's speeding is actually the result of the addition, or the acid addition. What do we end up with? Well, we end up with a stronger, or an increased reactivity electrophile. So really in these reactions, all we're doing is changing the nucleophile or altering the electrophile in some way to get the reaction to go faster. In our top case, the nucleophile reacts much quicker because it is negatively charged. The issue with that is because it is negatively charged, we now have to follow up with our acid as a step 2, okay, or a reaction step 2, because the acid would have neutralized our nucleophile, effectively quenching the reaction. Okay, so we want to do the acid as a second step. If we go through and look at our second reaction, speeding by adding, increasing the activity of the electrophile, we can add the acid right away because it's not going to quench the nucleophile. And that's because the nucleophile is not strong, or not negatively charged. Okay, so our reaction kind of runs through. You'll notice that we end up with a variety of steps, or different number of mechanistic steps, and a lot of that just has to do with the charge balance as you move through the reaction. But what happens if we go through and shift to weak nucleophiles, okay, or exceedingly weak nucleophiles? This can get a bit challenging. So before we even start into that, we want to do a brief word association game. So we're going to have a word pop up here, and then you're going to have a quiz. And that quiz, you just need to write down what comes to mind when you think of the word equilibrium. So take a second. Hopefully we're back. So this is an interesting issue that happens with equilibrium. Okay, it's not why would it happen, or it's happy, which we could really be putting in quotes. Okay, but it does it. Okay, our equilibrium just says it happens, and there's a variety of reasons why it happens. Okay, but it just happens, and it's not due to the energetics or the stability of things that we're used to seeing in organic chemistry. Unfortunately, you just have to deal with it. Okay? That said, okay, do not break your Lewis structure or curved arrow rules. Okay? We cannot exceed octets. We can't lose octets, particularly on electronegative atoms. Okay? I can't tell you how often that happens. Okay? So make sure you do not lose octets on an electronegative atom. That's huge. And then we'll always find a source of electrons and move them to some place that is lacking them. Okay, so we've got a variety of ways to kind of shift and move that around. It's just our standard mechanism rules. Okay? So if we go through to looking at water as a nucleophile, okay, since it is neutral charge, we're looking at one that's relatively weak. Okay, so if we, oh, way to give away the answer, we're looking at one that's relatively weak. It is still a nucleophile, so let's go through and address what could happen. Well, the negative, or our electrons, could attack our carbonyl carbon, which would break that open. the result is we would have popped open our structure. We would have had a negative charge here, and we would have a positive charge down here. The oxygen doesn't want to be positively charged, so we can do a sequence of acid-base reactions, which is really two steps, two mechanistic steps, to get to our final structure. Okay. That final structure is known as a hydrate because we added water across the pi bond. Okay? So it's been hydrated. If we consider this reaction, we would probably say it's not very likely to produce products, and that is largely based on this first structure, okay, or this first intermediate. Okay. Why is that first intermediate highly unlikely to form? Okay, so yeah, it's really, really charged. So how could we go through and improve the odds of running that very first step? Okay, well, just like we talked about with the mechanism, is we could go through and say, well, what happens if I changed my nucleophile to now being, instead of water, hydroxide? Okay, well, now when I run through that first step, I wouldn't have that positively charged, well, I'm just going to have to erase the whole thing there. I wouldn't have that positively charged oxygen, and that would kind of speed that reaction along, or speed that first step. The other option, I could have added an acid. The point of adding the acid is that that would then react with our negatively charged, or our partial negatively charged oxygen up top, protonating it, facilitating the backside attack, okay, or the attack from our water. Okay, so that, as an end result, does what to our top oxygen? Well, that actually gets rid of its negative charge, and we can stabilize our charged species that way. So two ways that we can kind of approach this, and that's kind of what we're hoping to see by changing our reactions. So since I just walked through that, I was going to break this down here, but we can leave it to you to try and attempt this. Okay, so what I want you to do is adjust this reaction, okay, and I want you to adjust it by making a stronger nucleophile. Okay, but remember, we can't change the product. The product must still come out the same. So do whatever you got to do to get the stronger nucleophile, and then answer the question. Okay, so hopefully what you were able to come up with is something along these lines, okay, where we have two mechanistic steps. Our hydroxide is being used as our stronger nucleophile. That strong nucleophile can do our attack. We'd form the sorry about that. We'd form the oxyanion, which can then be protonated by water or some other relatively minor or weakly acidic structure. If we wanted to use a strong acid, we could, but we'd have to go through and say this is step 1 and this is step 2. Okay, or reagent steps instead of mechanistic steps. But we end up with our final hydrate product. The other option is, again, going through and doing an electrophile. So speed up the reaction by making the electrophile more electrophilic. So again, as you do with the last one, take a swing at the next question based off of making the electrophile more electrophilic. And hopefully you're back with us, and what you came up with was something along these lines. We add that strong acid, which causes it to form our more reactive electrophile because we have resonance stabilizing that positively charged oxygen, which makes a very strong electrophile in that carbon because it is now positively charged, or formal positively charged, where it was partially charged before. We do end up forming a charged product, okay, which is not particularly stable, so water, our mild weak base, can be used to remove that super strong or that very strongly acidic hydrogen, and we end up again at our final product of the hydrate. Okay, so a slightly longer mechanism, but all in all, same general idea. Okay, well, water is a relatively benign nucleophile. What happens if we switched water to, I don't know, an alcohol? Okay, and at this stage, we'll just focus on any generic alcohol. Okay, so we have our R with our carbon structure. So if we wanted to do methane, we could do something along these lines. This still has a nucleophilic oxygen, and that nucleophilic oxygen can still go through and attack the carbonyl. And as we might have predicted from our hydrate reactions, is we probably would have ended up with something along these lines. And if we compare that to the product actually shown, well, they're not the same. Okay, and that's kind of a bizarre observation. So our alcohol is doing something in addition that is making this a little bit more interesting, if you will. Okay? So what we want to go through and do is break down the individual pieces and say, okay, what happened? How did this happen? Why could this happen? So identifying our nucleophile is going to become super important. Okay? So we do have our standard nucleophile outright in that first step of the reaction. You probably pulled that one out. But then how did we do the second step of the reaction? What was our nucleophile there? Okay, well, that's a good question. And since you got that one figured out, what was the electrophile in that second step of the reaction? Okay, we've got some interesting dilemmas popping up there. You'll notice I'm not telling you explicitly what the electrophile is because that one's a little bit more of a difficult question. You should have been able to figure out the nucleophile, and that the nucleophile was really just a second moiety, meaning just second molecule, of our alcohol. The electrophile still has to be that carbon, okay, but how does it act as an electrophile? And that is a tricky question. Okay? If we were going to predict which way the reaction occurred or which way the equilibrium favored, we would likely see it favoring the reactant. Okay? And that's a challenging question. So we'd have to go back and think about equilibrium. And in equilibrium, okay, we want to evaluate all of our conditions. Well, there's things like, I don't know, bond energy that we could go through and evaluate. And we'd notice that the ketone is actually favored over the alcohol in quotes. Remember, we have the keto-enol tautomerization, and that favored largely the ketone side, not the enol. So doing something similar to that, we would expect the keto form. We could also look at, I don't know, everybody's favorite term, entropy, and say, well, how is entropy coming into this situation? Well, if we remember from our 152 sections, we've got 3 molecules as a reactant, and we have 2 molecules as a product. Entropy favors more motion. The entropy favors the side with more pieces, which would be the reactant. Okay, so we've got kind of a complex problem going on here. Lots of little bits and pieces move into this. And so if we're going to try and push our reaction one direction or another, we have to be thinking about those conditions and how they can affect our end results. The last part of this would be, can the reaction be sped up? Well, just like we did with all of our nucleophilic additions, we can change the nucleophile characteristics, or we could change the electrophile characteristics. Okay? What I'm going to highly recommend you go through and do is take a look at the nucleophile characteristics, because that's actually one we'll talk about in more detail in class. The electrophile one is a really long one, and for that reason, we'll go ahead and break it down here. Okay, almost, not quite yet. If we add in all of our reactants, we can then go through and label what changed. We started with our carbonyl compound. We end at what's known as the acetal. This would be roughly equivalent, okay, to what we would have called the hydrate, okay, where we had the components of what appeared to be water on both sides of the equation. Here, or both sides of the structure. Here what we have is alcohols instead of water. The thing that's a little bit more interesting when we're comparing this back to the hydrate is that this appears to have happened twice. Okay? Well, the intermediate, if we will, the one halfway to becoming the acetal, would be the half acetal, or the hemiacetal. Halfway to getting there. So this doesn't all happen at once. We still go through the same basic mechanistic steps that we've been doing all the way through. Okay, so now let's go ahead and take a look at the mechanism, unless I forgot something else. Okay, good. So we want to tweak the electrophile. And as we talked about, the way to tweak the electrophile, okay, is to make it more electrophilic. So deciding between our two structures, which is the electrophile and which is the nucleophile. If we thought just general mechanism, okay, as soon as we add the arrow, that should now jump at us that we have the nucleophile here and we have the electrophile here. So I want to make the electrophile more positive. Well, to make it more positive, I need that carbon to become more and more positive. The way I can do that is by adding an acid. The acid will react with the other electron source, our oxygen, and cause that to be protonated. What is the result? Well, the result is that we now have a positively charged oxygen. And we have to be careful here. That does not make it the electrophile. Okay? Just because it is formally charged doesn't mean it's now our electrophile. We have to look at how the electrons around it balance out. And at this stage, while that oxygen may be positively charged, it can't accept more electrons. But it can steal them from another atom. And that loss ends up generating our stronger electrophile. Whoops. Okay, good. Didn't show anything. Ended up showing our, our stronger electrophile, and that we have resonance within that structure. Right? Our stronger electrophile can now react with our nucleophile, and we can end up producing our first product, okay, or our first intermediate. This is not a really good kind of product because we still have that charged oxygen, or we still have a charged oxygen. To neutralize that charged oxygen, it is going to steal electrons from one of its bonds. It could just as easily have stolen the electrons from the carbon, but then that takes us backwards. And because we're looking at equilibrium, we're concerned about what takes us forwards to see where we can get. And if we end up running into a dead end that's really, really bad, then we have to work all the way backwards to wherever we had a branch point. Okay. As another kind of secondary question that we can throw in here, why did we not look at breaking that R group off? Okay. So, if we wanted to get specific and show that something's picking up that hydrogen, we could show a second molecule of the alcohol, removing it, and we'd end up at our first intermediate, our hemiacetal. And this is where we might have stayed, okay, barring going to the lab. Yet when we go to the lab and run this, we find out that we end up with this full acetal. Okay, and that now begs the question, how did that full acetal come about? Okay, so we now have to start a next synthesis. We're starting with our hemiacetal. Okay, we're still under acidic conditions, and we still have our potential nucleophilic alcohol. Okay, well, our nucleophilic alcohol does not have a particularly good electrophile to react with. It can't immediately go in and kick anything out. Okay, why not? Well, bad leaving group and sterically hindered. Okay, so we need something to facilitate this. This is where the acid comes into play. Okay, the acid can come in again and protonate ROH, making a really good leaving group in water. Okay, could it have just as easily protonated the alcohol? Yes, yes it could have. Okay, equilibrium. It's a real SOB. You got to deal with it. Okay. So we now have a good leaving group. We could again try and think about how our nucleophile could chase out that leaving group. Okay, so it has to come in and chase that out. Okay, but as we just addressed in the previous section, there's a lot of steric hindrance there. That ain't going to happen. Okay, so what does happen? Okay, well, the water just leaves on its own. Okay, kind of as simple as that. Gone. This leaves us with a carbocation. Okay? Because I kind of ran out of space, we jammed that down below. That carbocation, before we can even say water can leave on its own, we have to evaluate it and say, is that a good leaving group? Okay, yes. Does it form a stable carbocation? Well, a secondary carbocation may not be the greatest. What we have to realize is we have resonance to stabilize this. Not only do we have resonance, what do we make when we do that resonance? Oh, snap, another carbonyl. Well, we know what to do with carbonyls. We can have our nucleophile come in, attack that carbonyl carbon. We end up generating, again, our acidic structure. Okay? A second molecule of our alcohol can come in and be basic enough to deprotonate, and we'd end up with our final acetal structure. So each of these little bits and pieces kind of stack and add to each other and eventually get us all the way there. Okay? And we haven't even said how successful is this going to be. We just said this can happen. We built a way to get there. Okay, so our big kind of nucleophilic addition using alcohols under acidic conditions is now summarized on this slide. Lots and lots of arrows, lots and lots of steps. However, if you really break it down and look at it, nearly all of these steps are acid-base steps. Okay? The simplest chemistry. The question really comes out, when do you do those acid-base steps? Right? And we're doing them at the appropriate time to ensure that we don't end up generating charges that should not be present in the solution. Okay? Which is really evaluating the strength of our acid and the strength of the bases as we work through it. The next big part I really want to draw your attention to is the far right, really acknowledging the relationship between our carbonyls and our acetals. Okay? Super important. You need to be familiar with this patterning, and I should have drawn this second alcohol there. How you kind of shift between these. Okay? To go one direction, we need 2 equivalents of our alcohol. To go the other direction, we need 1 equivalent of our water. Okay? And you might say, well, why do I only need 1 equivalent to chase off 2? Remember what we'd end up with? We'd have a carbonyl that could theoretically go up to the hydrate, but the hydrate is rarely stable. Okay? So we've got our bits and pieces. As you might expect, you will be expected to be able to predict what looks like what is an acetal, what is not a hemiacetal, what's a carbonyl, what's a hydrate. Okay, so you're on that full spectrum. Back to the question of which side is favored. Okay, well, this is a fun question to throw out. We've got 3 reactions here. So we're going to have a question pop up here in just a second. 1, 2, 3. I want you to go through and predict which direction is favored, or which side is favored, reactants or products for each of the 3 reactions. When we come back, okay, let's take a look at reaction 1. Okay, we've got 3 molecules to 2. We have a carbonyl. Okay, carbonyls tend to be more stable. So we might go through and say that our reactant is more favored. Okay, however, there was a clue given to you. If we take a look at the arrows, it's actually saying the product is more favored. So what else are we missing? Okay, it has to do with the stability of our carbonyl. Yes, carbonyls are in general more stable, but they also typically have carbons next to them which can inductively stabilize that carbonyl carbon. Okay? In this case, we only have hydrogens. What does that mean? The reactant is going to be favored, the product is going to be favored in this first reaction. Okay? Because we've stabilized that positive carbon better by putting in 2 oxygens. If we move to the next reaction, okay, you might already guess what's going on here. Okay? First, our reaction arrow tells us that the reactants are favored. Okay? And the question again becomes why? Well, we have that stable carbonyl. It is further stabilized by our carbons. okay, which would then suggest there's no real reason to drive to the product. Everything says that our reactants are stable. Okay, we have the entropic stabilization of 3 versus 2. We have our carbonyl stabilized by our carbons. Okay. Last one. Now this one gets extra tricky. Okay. We have again our ketone. Okay, so we might start to compare this back to that second reaction, with our reactants being more favored. But what is the additional difference? Well, our 2 alcohols are actually physically connected to each other, which then means when they go through to form our hemiacetal and then our acetal, that oxygen is very, very closely locked in. Okay? Taking a step further, if we look at the product, we have a 5-membered ring. Okay, and what do we say about 5-membered rings? Well, 5-membered rings tend to be relatively stable. Okay, so we've got some stuff now suggesting we shift to the products. But what about our good old friend entropy? Isn't entropy going to make an appearance here? Because entropy was one of the things that drove that second reaction to the reactants. Well, if we look at our reactants on the left, we only have 2 this time, and on our product side, we only have 2. So there is no entropic favoring here. Okay, we're really looking at the extra stability of that 5-membered ring really contributing to this, which then suggests that this reaction favors heavily the products. And indeed, it does. If we go through and look at our big summary, products favored for the first ones, reactants favored for the second, and our general rule when we're looking at our acetals, if you form a 5 or 6-membered cyclic acetal, that is favored in a reaction. Okay, we can reverse that, and we'll address that reversibility, but that is generally favored. And with that, you have the end of the video. Thank you for watching.